Can a moon truly vanish into thin space? It might sound like the kind of question that belongs in a science fiction movie, but surprisingly, the answer is yes. In the early days of astronomy, one of Saturn's many moons, an oddball called Iapetus, confounded astronomers by doing something no other celestial body had ever done. Sometimes it was there, visible in the eyepiece. And then, suddenly, without warning or reason, it simply disappeared. This wasn't a fleeting blink or a trick of the eye. The moon would literally vanish, refusing to show itself in telescopes that had seen it just a day earlier. What was going on? This bizarre disappearing act was more than just a curious glitch in observational astronomy, it was a clue to a much deeper mystery. Because the closer scientists looked at Iapetus, the weirder it became. Here was a moon that seemed divided in half. One side was as dark as asphalt, almost black, while the other gleamed like freshly fallen snow. It was like two worlds had collided and fused into one. And then, to make matters stranger, wrapped tightly around its equator was an enormous mountain range. A ridge so massive it encircles the entire moon like a stone belt. Its peaks reach higher than Mount Everest, yet its origins remain completely unexplained. Why would a moon look like this? What kind of event, or series of events, could carve a mountain chain so enormous and paint one half of a world in darkness while leaving the other side sparkling bright? And more importantly, what secrets does this bizarre world hold about the early days of our solar system? To uncover the story, we have to go back, way back, to the year 1671. That's when a brilliant astronomer named Giovanni Domenico Cassini looked up through a telescope at Saturn and noticed something peculiar orbiting the planet. It was a faint dot of light. A new moon. But this one didn't behave like the others. Using the telescopes of the Paris Observatory, primitive by today's standards but cutting edge in his time, Cassini tracked this mysterious moon. He noticed that when it was on the western side of Saturn's orbit, it was clearly visible. But when it moved to the eastern side, it faded, becoming almost impossible to see. Cassini, being a meticulous observer, took detailed notes. He even wrote that sometimes, after it began fading from view in a 32-foot telescope, they couldn't find it at all the next day with a bigger 45-foot one. What kind of moon behaves this way? Cassini eventually came up with an explanation. He proposed that this moon must have one hemisphere that was significantly darker than the other. And it must also be tidally locked, meaning it always shows the same face to Saturn, just like our own moon always shows the same face to Earth. So, depending on its position in orbit, the moon would sometimes show its bright side to Earth, making it visible. But at other times, we'd be staring at the dark side, and it would vanish into the blackness of space. It was a stunning realization, especially for the 17th century, and it marked the very first time astronomers had identified surface features on a planetary moon outside the Earth-Moon system. Cassini originally named the moon as part of a group called the Stars of Louis, or Sidera Lodoicea, in honor of King Louis XIV. But those names didn't stick. Later, the renowned astronomer John Herschel proposed a more fitting naming system based on mythological titans, the brothers and sisters of Saturn in ancient lore. And so, the moon was officially named Iapetus, after the father of Atlas and Prometheus. In mythology, Prometheus created mankind, so in a poetic way Iapetus was now seen as the grandfather of humanity. But this grandfather moon turned out to be anything but ordinary. For centuries, Iapetus remained a distant mystery. It was just a strange dot of light that astronomers occasionally saw changing brightness. Even the powerful Voyager probes, which revolutionized our understanding of the outer solar system in the 1970s and 1980s, only caught distant glimpses of Iapetus. Voyager 1 showed clear proof of the brightness contrast, confirming Cassini's centuries-old theory. But the images were low resolution, too blurry to reveal the strange details of this alien world. Voyager 2 passed by a bit closer and picked up something curious, a hint of a massive ridge near the equator. But even then the mystery only deepened. Everything changed with the launch of the Cassini spacecraft, named in honor of the man who discovered Iapetus. Cassini arrived at Saturn in 2004 and spent the next 13 years studying the ring giant and its bewildering collection of moons. Iapetus was a top target. In September 2007, Cassini performed a close flyby, skimming just 1,640 kilometers above the moon's surface. The images and data it sent back were breathtaking. Finally, we weren't looking at a point of light, we were seeing a full, textured world in all its strange beauty. What Cassini found only deepened the intrigue. For one, Iapetus is a lightweight. Its density is only 1.2 times that of water, which means it's composed mostly of ice, up to 75% in fact. That's why it's so cold and so light for its size. Its shape isn't perfectly round either. That giant equatorial ridge gives it an odd, walnut-like appearance. Scientists believe Iapetus doesn't have a liquid subsurface ocean like Enceladus or Europa. There's no evidence of tidal heating or recent geological activity. Instead, its surface is ancient and battered with craters, especially in the brighter areas like Roncevaux Terra, where massive impacts have left scars across the ice. Another strange thing about Iapetus is its orbit. It doesn't stick close to Saturn like most of its sibling moons. Instead, it orbits at a whopping 3.5 million kilometers from the planet, more than twice the distance of Titan, Saturn's largest moon. It takes 79 Earth days for Iapetus to complete one orbit around Saturn. And unlike most of Saturn's moons, which orbit near the planet's equator, Iapetus has a tilted orbit, about 15 degrees off the equatorial plane. This distant, inclined orbit might offer clues about its past. Some astronomers believe Iapetus didn't form in the same disk as the other moons. It may have migrated or formed in a more chaotic, early solar system environment. But let's talk about what makes Iapetus truly unforgettable: its surface. The moon is starkly divided. The leading hemisphere, the side that faces forward as it travels around Saturn, is shockingly dark. This region, called Cassini Regio, is coated in material so dark it reflects barely any light at all. Its albedo is just 0.03 to 0.05. To put that in perspective, that's as dark as fresh asphalt or coal dust. It absorbs nearly every photon of sunlight that touches it, making it look like a smudge of shadow drifting through space. Now contrast that with the trailing hemisphere, the side that faces backward in orbit, as well as the poles. These regions, known as Roncevaux Terra in the north and Saragossa Terra in the south, are incredibly bright. Their albedo is between 0.5 and 0.6, almost 10 times brighter than Cassini Regio. It's like looking at a world where one side is pitch black and the other side is blindingly white. In some parts near the equator, the boundary between light and dark is razor sharp, almost as if someone had drawn a line across the surface. In other regions, the transition is more gradual, with speckles and streaks of dark dust over the bright ice and vice versa. The contrast is so extreme, it's the largest surface brightness variation seen anywhere in the solar system. So what's causing this bizarre yin-yang appearance? For years, scientists thought it might be an internal process. Maybe the moon was spewing out dark material through cryovolcanic eruptions. In 1981, a team led by Bradford Smith analyzed Voyager data and proposed that dark material could be erupting from the interior, possibly flowing into craters and coating the leading hemisphere. It made sense at the time, but new data from Cassini would change everything. High-resolution radar and optical images showed that the dark layer in Cassini Regio is very thin, only about 10 centimeters to a meter thick in most places. And where meteoroid impacts have punched holes in the surface, bright, icy material is visible underneath. That meant the dark coating wasn't coming from inside the moon, it was being deposited from above. In 1982, another research team studied the spectrum of light reflected from the dark surface and found something interesting. The material was carbon-rich, similar in composition to a rare type of meteorite known as the Murchison C2, which fell to Earth in 1969. This suggested an external source, perhaps from elsewhere in the Saturn system. The prime suspect? A distant, irregular moon called Phoebe. Phoebe is large, dark, and orbits Saturn in the opposite direction, what's known as a retrograde orbit. Over billions of years, impacts on Phoebe and other small dark moons may have kicked up enormous clouds of dust. This dust, pushed inward by solar radiation through a process known as the Poynting-Robertson effect, slowly spirals toward Saturn, directly into the path of Iapetus, which orbits in the opposite direction. That's why the leading hemisphere, the side that faces forward, is so dark. It's sweeping up this retrograde dust like a windshield driving through a storm. As Iapetus continues its orbit around Saturn, a fascinating interaction takes place. Its leading hemisphere, meaning the part that faces forward along its orbital path, essentially crashes straight into a constant stream of dark, retrograde particles. These particles mostly come from Saturn's irregular outer moons, especially Phoebe. Think of it like driving on a highway through a swarm of insects. Your front windshield gets covered but the rear one stays relatively clean. In the same way, Iapetus' leading hemisphere ends up collecting much more of this cosmic bug splatter than the trailing side, which is mostly shielded by the moon itself. However, this alone doesn't fully explain why Iapetus' leading side is so dramatically darker than its trailing side. Nor does it explain the incredibly sharp, almost painted-looking boundary between the dark and bright regions. That's where another fascinating set of processes steps in: thermal segregation and water-ice sublimation. The dark material that builds up on the leading side absorbs more sunlight than the shiny white ice surrounding it. As a result, those darker regions heat up slightly more. Now, Iapetus is still freezing cold by Earth standards, but even a small temperature increase is enough to trigger a major effect. This slight warming causes the water ice in the dark regions to begin sublimating. That is, it skips the liquid phase entirely and turns straight from a solid to a vapor. Now, because Iapetus rotates incredibly slowly, taking about 79 Earth days to complete a single spin, the same amount of time it takes to orbit Saturn, the daytime side gets prolonged exposure to sunlight. That gives the ice plenty of time to warm up and sublimate during its long day. In fact, sublimation on Iapetus is surprisingly efficient. If its surface were made entirely of pure ice, scientists estimate over 100 meters of it would vanish due to sublimation over 1 billion years, faster than on any other of Saturn's moons. So where does all that sublimated water vapor go? Interestingly, it doesn't just float off into space. Because Iapetus has virtually no atmosphere to slow it down or trap it, the water vapor follows what scientists call ballistic trajectories. That means the vapor molecules basically leap across the surface like tiny missiles, flying long distances and eventually recondensing on colder regions, specifically on the trailing hemisphere and near the icy poles. These regions are already cooler because they reflect more sunlight, and that makes them perfect landing spots for the wandering frost particles. This sets off a self-reinforcing cycle. Dark areas warm up, lose their ice, and as the remaining dark material becomes even more concentrated, they get darker still, absorbing even more heat. Meanwhile, the bright areas stay cool, accumulate more frost, and get even brighter. This contrast intensifies over time. It's a runaway feedback loop that sharpens the division between the dark and bright hemispheres even further. Over millions or even billions of years, this process has carved an incredibly dramatic high-contrast appearance onto Iapetus' surface, with a bold split down the middle that looks too perfect to be natural, but is in fact one of nature's most elegant tricks. So, the bizarre two-tone look of Iapetus is the result of two processes working together. External dust coating it from retrograde moons like Phoebe, and internal processes like ice migration driven by sunlight and surface temperature differences. It's a beautiful demonstration of how different planetary forces can cooperate to sculpt something truly unique. But hold on, the weirdness doesn't stop there. Because Iapetus has one more bizarre feature that might be even more mind-bending than its two-tone surface. A giant ridge like a wall of mountains running along its equator. Yes, you heard that right. As early as the Voyager 2 mission, scientists noticed a strange bump circling Iapetus' middle. But it wasn't until the Cassini spacecraft got close that the full extent of this feature was revealed. Known as the Equatorial Ridge, it's a mountain chain that stretches about 1,600 kilometers, nearly halfway around the entire moon. At its base, it can be about 200 kilometers wide, and some parts of it rise nearly 20 kilometers above the surrounding surface. That's more than twice as tall as Mount Everest. And even more astonishingly, this ridge sticks almost exactly to Iapetus' equator, like a seam around a baseball. In Cassini's close-up photos, the ridge gives Iapetus a distinct shape, almost like a walnut with a swollen middle. And scientists have been trying to figure out how something so unusual could have formed. One of the most widely discussed theories is that the ridge is a leftover feature from Iapetus' younger days when it may have been spinning much faster than it does today. According to this idea, early in its history, perhaps shortly after it formed, Iapetus might have completed one rotation in just 16 hours. That's lightning fast compared to its current rotation rate. This fast spinning would have caused the moon's equator to bulge outward due to centrifugal force, especially since Iapetus was likely still warm and partially molten at that time. As it cooled and solidified, that bulge would have frozen into place. Then, over millions of years, gravitational interactions with Saturn caused Iapetus' spin to slow down until it became tidally locked, rotating once for every orbit, like our moon does with Earth. With the spin gone, the centrifugal force that once supported the bulge disappeared, and the solid crust began to sag. But since the bulge was already frozen in place, the crust couldn't fully relax. Instead, the material slumped downward and gathered along the equator, eventually forming the massive ridge we see today. This theory fits well with several features. It explains why the ridge follows the equator so precisely and why it appears to be so ancient and heavily cratered. But it does have some weaknesses. For one thing, it requires Iapetus to have spun at incredibly high speeds, potentially near the point where the moon could have started breaking apart. And it also assumes the moon solidified while still maintaining that high-speed rotation, which isn't guaranteed. Another fascinating theory proposes that the ridge isn't a bulge that collapsed, but rather a pileup of external debris. According to this idea, Iapetus may have once had a ring system of its own, a small disk of rocks or dust orbiting it near the equator. This could have happened if Iapetus captured a small body or suffered a large impact that ejected debris into orbit. Over time, if that ring became unstable, perhaps due to slight changes in Iapetus' orbit or its gravitational interactions, the material would have rained down directly onto the moon's equator. Because orbital mechanics force ring systems to align with a planet or moon's equator, the material would have hit in a very narrow band, creating a linear pileup of rock and ice, the ridge. If the ring's composition was similar to the dark material from Phoebe, this could also help explain why the ridge is mostly located within the already dark Cassini Regio. Some simulations suggest that even a small moonlet orbiting within Iapetus' Roche limit, the distance within which tidal forces from the moon would tear a body apart, could provide enough material to form the ridge if it broke apart. This debris ring theory is elegant and helps explain the ridge's precise location. But it still has challenges. For one, we've never seen a moon with a natural ring system, so this would be a unique event. And exactly how such a ring would have formed and then collapsed remains an open question. Still, it remains one of the more plausible ideas in the mix. Other explanations, like tectonic activity or upwelling from deep inside Iapetus, have a harder time accounting for why such a huge feature would be confined so strictly to the equator and why it's so long and narrow. A single massive impact seems unlikely too, because such an event would probably produce a round crater or a more chaotic disruption, not a clean, straight ridge. Cassini's high-resolution images showed that the ridge is composed mostly of icy crust and that it's ancient, heavily cratered and battered by time. Some sections even show signs of landslides and collapse, suggesting the ridge has been slowly degrading ever since it formed. Whatever process created it, it must have occurred early in Iapetus' history, probably within the first few 100 million years after the solar system's birth. That makes the ridge not just a structural oddity, but also a time capsule, an ancient record of events that shaped this moon when it was still young and active. It's one of the strangest, most baffling features in our solar system, and to this day scientists are still debating its true origin. So, where do we stand in our understanding of Iapetus? Thanks to the Cassini mission, we know a lot more than we used to. We have solid evidence that the dark side is coated with dust from retrograde moons like Phoebe, and that sunlight and sublimation work together to create the stark contrast between hemispheres. We've captured incredible high-resolution views of the equatorial ridge, mapped Iapetus' shape, measured its gravity, and studied its surface composition in ways that were unimaginable before. But mysteries still remain. What exactly is that dark dust made of? Is it organic-rich material? Why does the ridge exist and why is it so perfectly aligned with the equator? Could Iapetus have once had a ring system? Or did it spin so fast it nearly tore itself apart? We won't know for sure until we go back. And unfortunately, as of now, no missions are planned to revisit Iapetus in the near future. For now, many of its secrets remain locked away beneath its ancient, icy surface, which somehow feels appropriate. As we said at the beginning, Iapetus was the ultimate cosmic vanishing act. A moon that disappeared and reappeared in the telescope's eye like a magician's trick. And like any great magician, it refuses to give away all its secrets just yet.